Okay, to conclude, Rolle's theorem. Conclude the section on Rolle's theorem. We'll see another canonical example. I don't know how this would be implemented as a question in the exam. Maybe as a multiple choice. Let me write down the problem and I'll explain what I think will happen if this is something like this is asked in the exam. So we're asked to show that f of x equals to x cubed plus 9x minus 4 has exactly one real root. So a variant of this problem that you may encounter in the exam or web assign is they may ask you, they may give you a function like this one and ask you and give you some alternatives. So what can you say about the function f? It has one real root, it has two real roots, it has three real roots, and you'll have to reason as follows. So you just have to perform this analysis to conclude that there's only one root. So f of 0 is less than 0 because it's equal to minus 4, and this is less than f at 1. So I don't know if you remember, but we saw the intermediate value theorem, and we saw that before the first exam, and how to apply it to find at least one real root. So you plug in two values here, 0 and 1 are convenient points. If not, remember that x cubed when x becomes very positive, is able to overcome all the other terms here because it's the highest power. It becomes very positive. So eventually this expression here will be very positive. So the point you choose, it's a matter of preference. These 2 points are very convenient, so 1 and 0. And so since 0 is in between f of 0 and f of 1, you know, by the IVT, there is a point C or X. I mean, let's just use or X naught between 0, 1, 0, 1, such that f of x naught is equal to 0. So there's at least one root, one real root. There is at least one real root. Can there be another one? So that's a question. Can there be another one? The answer is no. No. If there were another one, there were another root x1, well, that means point where f of x1 is equal to 0. Rootable, so that means f of x1 is equal to 0. Then we would have that the hypothesis of Rolle's theorem will be satisfied. We have 2 points, x naught and x1. They're both different. I mean, if not, there's the only root. Then we would have, then by Rolle's theorem, there would be point in between these two such that the derivative f would be equal to 0. And here I don't need to explain any further that f of x being a polynomial is differentiable everywhere, so that part of the satisfied hypothesis for applying Rolle's theorem is already met. But this can never be the case. So if there is another root, then you can find a point in which f prime vanishes. But let's take the derivative of f. So f prime of x is, and this is the same thing for all these kind of problems, 3x squared, you get 3x squared plus 9. And whenever you have to deal with this kind of problem where you're asked to do something like this, that rings a bell for you, you just try to see. If we have two roots, then Rolle's theorem applies. So what's going to happen with the derivative? This is what's going to happen. You compute it, and you notice that this is never negative, 3x squared, and this is positive. So in fact, f prime is always positive. So it can never be any value c such that f prime is equal to 0. Because in fact, f prime is always positive. So this is a contradiction. So the conclusion here is that there's no such value. So there isn't another root in R. So there's only one. We proved that there was one by using the intermediate value theorem, and assuming that there's another one, we reach a contradiction. So this cannot be the case. Okay. So the application of the theorem is always like that. It's assume that there's another one, you will find that will contradict Rolle's theorem. So whenever you take the derivative of that function, you will find out that the derivative is always negative or always positive. Okay, so that's it. So that ends our Rolle's theorem section.